I'm standing on the largest volcano in the Pacific Northwest. It's called Newberry Volcano, and it's as big as the state of Rhode Island. Right here is the site of an experiment that's aiming for a breakthrough in geothermal energy. This experiment is one small step in the high-risk, high-reward world of next-generation geothermal. The goal is to replace fossil fuels with this always-on renewable energy. The challenge is getting it to work. To access geothermal energy, you need three elements: heat, permeable rock, and water. The water flows through the gaps in the hot, permeable rock, transferring heat from deep underground to the surface. That's geothermal energy. The world's first geothermal resources were the rare places where those three things just happened to come together naturally, like hot springs or geysers, found in places like the US Mountain West. Early projects were extremely simple, pumping the water into buildings for heat, hot baths, and apparently making knockoff chicken broth. That's right, according to this 1870 Idaho newspaper article, this hot springs water, when seasoned with salt and pepper, cannot be distinguished from the best chicken soup. Throughout the 20th century, countries all around the world, like Italy, Iceland, and the US, started using geothermal energy to produce electricity, using the steam to power turbines. This form of energy has one big benefit over other renewables. And to understand, let's compare a geothermal plant and a solar farm, each capable of pumping out the same amount of power. On the solar farm, let's say it's only really sunny for about 5 hours a day. This means that every day, it only produces 20% of its potential. The geothermal plant, on the other hand, can basically produce full power all day, every day, which makes geothermal a really useful kind of energy. It's got the same always-on benefits of a fossil fuel power plant, but it's a renewable. So people were understandably excited about geothermal.
We hope that by the year 2000, we are going to be able to get on the line maybe as much as 75,000 megawatts. That would supply the needs of 75 million people.
And look at this graph. You can see it taking off in the US after the 1970s energy crisis. But for all its benefits, geothermal energy has only ever played a small role on our grid. And to understand why, let's go back to that solar farm. To build this solar farm, you need to find sun, and you do that by looking up. But for the geothermal plant, I need to find the rare spot that has all three of those geothermal ingredients hidden under miles of rock. Then I need to pay for expensive equipment and labor and go through years of permitting just to get the plant up and running. So despite all of its benefits and the almost limitless energy in the earth, it's hard to make a project pencil out. Because of these challenges, geothermal energy started to slow down in the 1990s. The industry needed something to change. That change? A new process known as enhanced geothermal. Instead of relying on places where all three of those geothermal ingredients come together naturally, enhanced geothermal allows you to tap into heat even if you're missing the other two ingredients. It works by injecting high-pressure water into the ground, forming a network of little cracks for the water to flow through and carry heat back up to the surface. It's a similar idea to fracking, just with a lot less pollution. This really opens up the potential for geothermal. To put things in perspective, the US currently produces about 3 gigawatts of geothermal electricity. Enhanced geothermal could theoretically generate more than 5,000 gigawatts of electricity. That's way more power than all of the fossil fuel plants in the entire country. So why isn't enhanced geothermal powering the world? Well, despite a few successful pilot projects, the problem, once again, is money. Right around the time that people were getting serious about enhanced geothermal, another energy transition happened.
With the advent of natural gas, the price of solar panels going way down, wind technologies coming along, everything sort of changed in about 2014, 2015. The goalposts changed. The marginal price of energy, especially renewable energy, just dropped.
This is Jeffrey Garrison. He's a VP at the geothermal company Alterock. Alterock was one of those companies trying to build on the promise of enhanced geothermal, only to be caught off guard by that wave of cheap gas and renewables. In order to be competitive, the only option they saw was to build an even hotter enhanced geothermal project. And that's what brought them to Newberry Volcano.
There's a very large magma body underneath it. It contains a tremendous amount of heat.
Alterock wanted to reach temperatures of 400 degrees Celsius, what the industry calls super hot rock. At this temperature, you get way more energy, and you extract it more efficiently. In a normal location, you'd have to drill down about 8 miles to reach these kinds of temperatures. But at Newberry, it's so hot that you can reach these temperatures at a quarter the depth. Alterock saw this as the perfect testing ground for super hot geothermal energy. I came to Newberry to witness the start of this experiment, a flow test. It's a simple test to make sure everything is in order before they drill down all the way to the super hot rock. But because of an unexpected snowstorm, it was delayed.
It's cold.
And we had to head home. A few days later, I got a video in my inbox. The flow test was a success. It represents the very first step in this long moonshot. And now, the real work begins. If Alterock is going to reach those super hot temperatures beyond Newberry, they're going to need to drill deeper. And that's really hard to do with conventional drills. Instead, they're hoping to use another type of new technology that sounds like science fiction. A heat ray to melt rocks, called a millimeter wave. It's kind of like a laser in a different part of the spectrum.
This is not fantasy, because I did blast through a basalt rock, okay?
The idea came from Paul Waskoff, a fusion scientist at MIT. In his research, he'd seen the waves accidentally melt holes in lab equipment. And years later, he started to study millimeter waves as a way to melt rock. After a decade of research, he's now working with a geothermal company called Quaise to test these millimeter waves for geothermal drilling. They're doing tests at Oak Ridge National Lab, essentially melting holes in rock. Eventually, Alterock hopes to test these millimeter waves in the real world at Newberry. And if they're successful, this new heat ray might make it more feasible to reach these super hot temperatures anywhere. Now, Alterock and other geothermal companies like it have a long and challenging road ahead. But they also see a big reward.
Yeah, we're talking about replacing every coal plant in the country or every natural gas plant in the country with geothermal. We can do that. That's the scale of resource we have at hand.
It's certainly not guaranteed to succeed. Odds are there will be a lot of failures along the way. But there's so much heat in the earth that today's geothermal energy is just the tip of the iceberg.